Well, welcome back, guys, and I do hope as ever you and your family are keeping well. What we're going to look at today is refractive index, but we're going to look at it in a slightly more mathematical way. So let's see if we can say what refractive index is. Okay, well, how much a light wave bends, so how much light, but remember it can be other waves as well. Now that bending is a change in direction. I put my little graphic up there to remind you. Okay, the cause of it, yeah, if you remember, is change in speed. So I'm trying to put a lot of ideas up here to remind you. Okay, so how much it bends, changes direction or changes speed when going from one medium to another one. Medium is the material it travels through. Depends on this idea, the refractive index. So we need to give the refractive index a symbol so we can use it in formula, and it's given the symbol little n. Okay. Now, there's a lot I can say about this, but the first thing is, remember that we're going from one medium into another one, or from one medium to another one. And I tend to use the term optical density. It's not used in the book, I don't think, but it's kind of how the waves, or I'm going to talk about light from now onwards, feels when it goes from one material to another one. Now, in most situations, we consider the material on the outside, the medium on the outside, to be so optically undense. In other words, it doesn't slow down light much. Air, we consider it to have the same properties as a vacuum. In other words, we consider the light to be coming in, check that it's air, okay, coming in at approximately the speed of light in a vacuum. So the major change happens when it enters the more dense medium. I will just say at this stage, think about this as a pair of swimming goggles, tricky to visualize, but the outer medium then will be water, and what I've drawn inside the block there will be air. So sometimes the densities are the other way around. Now I'm going to try and stick to the word refractive index now. Okay, so what we'll do is we'll have a look at what this n is and whether it has dimensions, units or not. So I told you that n tells us something about the speed of waves or light through media. And so I'm going to say here for a material. Now when I say for a material, I mean a very specific single material. I don't mean between the two. So for example, if this was a glass or plastic block, I'm going to show you what the refractive index is for that material. Well, it's actually quite simple. It is just the ratio of the speed of light. Do that with a blue pen. So n, the refractive index, yeah, is the speed of light and it's the ratio of the speed of light to the speed in that material. So divided by the speed in the material, or the speed in the medium. Okay, now I've got to be a little bit careful here because we'll call the speed in the material V. And then the speed of light, this is a little bit annoying. The speed of light is given the symbol c, but it's a small c. Okay, and we're going to be a bit careful about that because unfortunately we're going to come across something called the critical angle fairly soon in this lesson, and the critical angle is given the letter C as well, but I'm going to be really careful to give that a capital C. So let's just remind ourselves of these numbers. If it's for a single material, the refractive index, then we're comparing the speed of light in a vacuum, okay, so 3.0 times 10 to the 8 meters per second, to the speed in the material. And the speed in the material will always be slower, okay, unless it's a vacuum as well. So this number, n, will always come out as a number bigger than 1. So just to sort of demonstrate that, quick example. If n equals 1, we're in the fairly obvious situation where we calculate n as the speed of light, small c, over v. And if that equals 1, then it's pretty obvious that the speed in the medium is the same as the speed of light. In other words, there's no slowing down. And if there's no slowing down, the wave will go in a straight line. Okay. But it's worth pointing out that the sort of values, typical values we get for refractive index, n, has a range. You can look this up, and it's not quite what I'm saying here. But when you do your calculations, you should get n in the range of about 1 up to about 3. There are materials that have higher refractive indices than 3. But we don't need to worry too much about those. And we're certainly not going to get into the realms of, is there such a thing as a negative refractive index? Okay, we'll just stick with the A level for the time being. Now, I finally wanted to point out, what are the units of n? Well, if n is meters per second divided by meters per second, or T to the minus 1 divided by LT to the minus 1, then you'll notice that the refractive index is dimensionless. In other words, n here has no units. So now let's look at a couple of examples of this. So the thing we typically do is, and I'm a bit old-fashioned, is we draw what we call glass blocks. You can imagine it's a window or something like that, it doesn't matter. But what I'm trying to represent here is outside we've got air, and then inside the box I'm drawing, it's a denser material to the light. I did say I'd stop saying that. It's one that light will go through more slowly. Okay, and typically we use plastic or glass blocks to demonstrate this in the lab. But it could be air to water. So there we go. There's our materials. And on the first diagram, what I'll do is I'll draw a ray of light coming into it. Okay, so here's our ray of light. By the way, these diagrams are always reversible, so you don't necessarily need to draw the arrow, the direction of the light. But we'll have the ray coming in like that. And then I do hope you remember that what you do here is draw on the normal to the ray. The normal to the block surface. I'll just say that again and get it right. Where does it hit? Where's the surface that it hits? Draw a line at 90 degrees to that. Okay, the normal. So, pen smudging a bit there. There we go. Okay, so there's the ray coming in. And you know that if this slows down the light, it will bend towards the normal. Okay, so there'll be a refracted angle like this. And then we won't deal with what happens when it comes out. We'll just look at this case. So let's say that out here n equals 1. So we're basically saying the light is going at the speed of light. It's air, it behaves a bit like a vacuum. And let's say the refractive index of this material is n equals 1.4. Okay, remember it's got no units. So to work out what the speed of the light is here, what the speed of the light will be here, we're saying it's coming in at c, okay, because it's basically an air in a vacuum, then n equals c over v, and therefore v, the speed of the light through this material, is c over n. And it's at this stage that I really want you to think about it. Oh yeah, I get it. The refractive index is a number bigger than 1. So the speed that it comes in at is going to be the speed of light divided by a number bigger than 1. So it's going to reduce that speed. So here we've got the speed that it will go through the glass block will be the speed of light, 3.0 times 10 to the 8, divided by the refractive index, which is 1.4. Where did I get that 1.4 from? I just made it up for this example, but obviously if we know the material, we can look up the refractive index. There's a whole series of them for different types of glass before you even get going. And if you work that out, the velocity in this material will be 2.1 times 10 to the 8 meters per second. Notice, just when you do your calculations at A-level, that it is smaller. Okay, it's a smaller number. Now, what would happen if we shone light into a material that had a refractive index of 2? So, here's some light coming in. Now, I'm not worrying too much about the angles at the moment, but I will just draw the normal on, because it's quite important that you remember that the angles are always measured from the normal. So there's an angle here, an incident angle and a refracted angle. We'll draw the direction that the light comes in. Okay, I will just guess an angle that it turns through, like that. Doesn't matter if the two diagrams look slightly similar. Okay, I'll put an arrow on there to show the light rays going that way. That's its speed. That's the speed it's coming in at. The speed of light, because we're considering that to be air. Okay, and if we make the refractive index of this material 2, okay, I don't think I need to do masses of maths on this. You can see that if the refractive index is 2, then it will be the speed of light divided by 2. So the velocity we get here will have to be half the speed of light, 1.5 times 10 to the 8 meters per second. So let's look at this a little bit more mathematically, and we're going to look at something called Snell's law. I could go to town on whether Snell actually did this work. It was probably done many, many, many years before, and his name wasn't, I think it was Snellius, but you know, whatever. Physicists who do this work call it Snell's law, and it's about looking at how the angles, the angle of incidence here and the angle of refraction, relate to the refractive index. Okay, so to do that, you might guess I'm going to have to draw a glass block again, so bear with me, but I'd like you to see how we put this together a stage at a time. So here's our material, and I'm going to make it a bit tougher this time. I'm going to suggest that maybe this is a glass block with a refractive index, and it's in another medium out here, and that medium isn't a vacuum, it isn't air. Maybe it's a glass block in water or something like that. Okay, so we'll draw a light ray, and just watch what I'm doing here. I'm sort of up to something to make the teaching clear. Okay, so there's the light ray, and I'm going to put the normal on because we're going to need this now, because we're going to have to measure some angles. So find where it hits the surface, find 90 degrees to that point. So that is the normal to the surface. I'll just ink that in a little bit better. Okay, now I did say that ray diagrams of this kind are reversible, so just to be a pain, why don't I do that? That shouldn't worry you in the slightest, okay? You've got angles here that you can look at, and we're going to be very careful not to name these angles. The angle of incidence and the angle of refraction, because it's going to get a little bit complicated. So to solve that problem, what we're going to do instead is say, okay, here it is. Yep, that ray travelling that way, and we'll call that angle 1, theta 1. Here's the ray coming out, and we'll call that angle 2, theta 2. Okay. Now, I'm suggesting we've got two different refractive indices here. Okay, and I'm going to, for the sake of the example, I'm going to make neither of them 1. Okay, just to make it a little bit harder. So this one, this material with its angle, theta 1, has a refractive index of N1, and this material out here has a refractive index of N2. Okay, so we've got everything we need to do to explain what the equation is for Snell's law. Now, it's really quite interesting. Okay, Snell's law, or should I say the equation that allows us to talk about Snell's law, is if you take the refractive index in the first material, okay, and multiply it by the sine of this angle, okay, it will be equal to the refractive index in this material, okay, N2, multiplied by the sine of this angle. Now, I've got to be careful, which thetas are they? Okay, this side of the equation is all to do with that theta, and this side is all to do with this one, okay? So, very quickly look at the diagram. I think I made a good job of that for once, okay? And you can see that this side of the equation is all about what's going on here, and this side is what's all about going on here. Now, you could swap that round, of course. If you had the ray coming in, there's nothing to stop you calling this theta 1 and this N1. It doesn't matter, okay? So, we can use this equation to find out what the refractive index is if we know, if we know all of this bar one thing. So that's what we're going to do next. So let's use the Snell's law equation now to do a quick example. So we've got the block here, and I've got two refractive indices, and I've made sure that N2 is not 1. I've tried to make it a bit more complicated than that. I could set this up in the lab without any trouble at all. I could fire in a red light beam or a laser beam, and I could easily measure these angles, okay? And I could look up what the refractive index is of this medium here, okay? And it's clearly not air or a vacuum because it has a refractive index of 1.2. So I've made up some numbers here. So we've got the angle here as 25 degrees. The refractive index of this material is unknown, so we're trying to find the refractive index of this material. Okay, theta 2 outside is 45 degrees, just made up number, and the refractive index here is 1.2. So light will go, slower than the speed of light in this material. So let's see if we can work out what N1 is, the refractive index of this material. So we've got our Snell's law equation. And just before I do the maths on this, which is really easy, of course, just look carefully that if I do N1 over N2, yeah, it's sine theta 2 over sine theta 1. So N1 over N2 is sine theta 2 over sine theta 1. They're sort of back to front, just something to notice there. Okay, so what is the unknown N1? So N1, the refractive index in this material, is going to be equal to this lot, N2 sine theta 2, all divided by sine theta 1. Okay, so let's put the numbers in. N1, the unknown refractive index, yep, is going to be N2, which is 1.2, times by sine 45. It's that angle. All divided by the sine of 25. Oh, I've made a smudge of that, so let's make a better job of that one. Okay, not a permanent pen. Sine 25. And if you bash that out on your calculator, N1 will come out as no units, 2. Okay. Now, as soon as you see 2, you think, oh, that's interesting. Okay. 2 means that compared to a vacuum, yeah, compared to a vacuum, not compared to this material, compared to a vacuum, the speed of the light in here is half the speed of light. So I'll just put a little annotation here. You'll notice that this here is a half, small c, the speed of light. So there we go. There's an example using the Snell's law equation. So what we're going to look at now is something quite interesting, taking into account refractive index. We're going to look at total internal reflection. Now, I hope you've seen this before, but if you haven't, I'll do it in detail anyway. And it's something that people just seem to completely miss. It's a really weird property whereby, well, let me try and give an example. I don't know if you've ever been diving and you've been under the water, and you've looked up at the surface of calm water at a very, very sort of steep angle, and you don't see out of the water, okay? You see straight back down into the water. It's where light travels through a more dense material and actually never gets out of it. But that more dense material is completely transparent. So this is a little bit illogical. So before I explain it in detail, it is the reason why diamonds sparkle. And I don't have many diamonds, as you might guess. But if you think about it, a diamond ring has a diamond in a metal kind of container, the setting. And so if the light goes into the diamond, why doesn't it just refract and hit the metal casing? How is it can go in and come back at you? Okay. Cat's eyes in the UK are an example of that sort of thing. Okay, rainbows. Now, this is a bit of a tricky one, but and you get good at this if you're a physicist, finding where rainbows are and when they'll happen. Okay, if you think about it, you'll spot this next time you see a rainbow. You need. I'm going to turn my back to the projector. You see a rainbow here where it's raining, but the sun is behind you. Okay. So what's happened there is the light has actually gone into the water droplets, which are a higher refractive index than the air, and they've actually reflected off the inside of the totally transparent water. Okay, and finally, the absolute classic example of total internal reflection is its use in fibre optics or optic fibre. I'm going to show you some of those in a few minutes. So, for total internal reflection to happen, and I'm aware I have to explain it and show it to you in a minute, but I'm going to set some rules, so where you hope to find total internal reflection. Okay, there's a couple of situations that have to be true for it to happen. So, the light must be going from a higher to a lower refractive index. That's really important. So the light, the waves, must go from a high N to a lower N. Okay, that's the first kind of rule. And if you have that situation, okay, you might be able to set it up, well, you will be able to set it up, so you can get total internal reflection. Okay, I've made the mistake of this before now. Okay, you do not get total internal reflection when the light goes from a less or lower refractive index to a higher one. So when you look at a shiny lake or something, that is not total internal reflection. It's a large amount of partial reflection. Okay. And there's one other thing that I hinted at before, that the angle that the light hits the less dense medium. Okay, so the angle the light hits the lower N boundary must be bigger than a certain value. And we call that the critical angle. Okay, watch C. Capital C for the sake of this. Okay, so I'll draw some diagrams in a second, but what you imagine is a light ray maybe travelling through a glass block, and it's going to hit that glass block boundary with a lower N, okay, a lower refractive index. And if it hits it, remember the normal, if it hits at an angle that is such that it's bigger than a specific angle we're going to talk about in a minute, the critical angle, then you can guarantee that that light will obey the laws of reflection and will never exit that totally transparent material. It's a really weird effect, and I will show it to you in the laboratory in a second. So let me see if I can demonstrate what I mean by the critical angle. And I don't know how many times in my career of nearly 30 years have I drawn this diagram. Okay, I've chosen, just for the sake of it, and I'll explain why in a second, to draw some glass blocks here. They're meant to be identical, okay, the same refractive index. And I've chosen to draw a semicircular one, okay? It doesn't have to be semicircular, but you'll see why that's quite a clever thing to do, okay? And what we'll do is we'll shine some light into the first one. So here we go. And I'm just going to aim for that point there. So I'll shine it in at that angle. Now, you might just see why I've chosen a semicircular glass block, because that's a radius. And if that's a radius, then that will go in at 90 degrees to the surface, in other words, along the normal. So it just goes straight in. It slows down, but it goes straight in. Let me draw the normal on. Okay, so there's the normal. Perhaps I put that a little bit to the right, but never mind. Okay, and let's have the ray refracting through an angle. There we go. Okay, so you'll notice that this ray comes in and bends away from the normal. So we know something about the refractive indices here. We know that N2 out here, that's this material, and we know that this is N1, and we know in this case that N1 is greater than N2, okay, because as the light leaves the glass, it bends away from the normal, so it's speeding up. Okay, and you can see the two angles there. Now, there's something interesting about these angles. Okay, this angle here, so theta here, is such that the light will go in, I'll draw an arrow on it in a minute, and will cause refraction, not reflection. Now, we're hunting for total internal reflection because we have got a less dense medium here, or a lower refractive index, so we're set up to find that. But unfortunately on that diagram we get refraction. So this angle here must be smaller than, the critical angle. Okay, and I'll put the critical angle like that. Now, my GCSE students find this particularly hard. Let's just carry on with N1 and N2. Okay, and I'll now do the second diagram. Now, the second diagram, I'll come up here to do it, in fact. I'm going to turn this angle up and make it bigger and bigger. Now, I do a lot of hand waving with this. I really need another ruler, but my hand will do it. Okay, straight through, straight on. That angle bent. That angle bent. This angle bent. Can you see what's beginning to happen? It's beginning to happen. If I go any bigger than that angle, this ray will scoot along the surface, back to there. Okay, so what happens if we don't go straight in, we don't go at that angle, but we go at a bigger angle? It's not 45 degrees necessarily. Okay, I hope you're all happy with the fact that that ray will go straight in there because it's along the normal. So there we are, there's the ray going in. I'll try and draw the normal properly this time without smudging everything. There it is. Okay, and we've opened up this angle. We've made it bigger, maybe twice as big. And of course the ray coming out now will be, well, I've got it just right, scooting along the surface of the block. So there it is, doing this sort of thing. Okay. Now, if that's the case, then if we make this angle just a smidgen bigger, that ray is going to get stuck inside this material. And it's staying in the same refractive index, so it can't slow down or speed up, so it's going to reflect. That's that diagram. But just bear with me here. We know that this theta here is equal to the critical angle. So theta critical. Okay. Now, I could write that as theta here is equal to big C, the critical angle. Just for fun, let's go for a bigger angle. I know I'm going to smudge everything now, probably. There we go. Okay, now I hope you can see, and this is a bit I find difficult to explain to GCSE students, that if I pull that any further, any larger, this ray is going to be stuck in this material and it's going to be regular reflection. Oh, hang on, but not totally regular. It's a reflection where a ray hits the boundary between a bigger n and a smaller n. Okay, it's an angle bigger than the critical angle, so you will get total internal reflection. Now, I usually mess up my angles here, but let me try my best. Is that any good? Okay, there we go. So I'll draw the normal on, and you're now in the realms of this angle here. That one is equal to that one. They're both the same, and if those two angles, I'll just put theta here, theta 1, theta 2. If theta 1 equals theta 2, then we are in that special case. Okay, theta 1 is greater than the critical angle, and I'll be a little bit lazy. What's this process called? Total internal reflection. But just before we finish this bit on the critical angle, I'd like to show you something quite clever. Okay, I'm going to look at the special case where we just get total internal reflection. So I'm homing in on this diagram here. Okay, now we remember the Snell's equation, n1 sine theta 1 is equal to n2 sine theta 2. But there's something really interesting happening here. Firstly, look at theta 2, it's 90 degrees. So that sine is going to turn into the number 1. The second thing, and this is quite interesting too, is when we're outside here, we normally consider that to be air or a vacuum, typically air in my laboratory, of course. So N2 has the light basically going at the speed of light. In other words, N2 is the number 1. Okay, so if I rewrite that for this diagram only, of course, because we have to have the 90 degrees, N1, which is the refractive index of the thicker material, as it were, sine of the angle in that material, is going to be equal to N2, and we said that's out here. It's basically air or a vacuum, so that's going to be 1 times by the sine of 90. Oh, well, that's going to be 1. Okay, but what is this angle? Well, if we made that 90 degrees, then it must have been the start of total internal reflection, so theta 1 must be the critical angle. So we can rewrite this as N1 sine of C, the critical angle, is equal to 1. Okay. So I'll go over here. Yeah. Sine of the critical angle is equal to 1 over n. And therefore, the critical angle will be equal to the sine to the minus 1 of 1 over n. And you'll see how clever that is, because you often know this number. You often know the refractive index in this material. So if you know the refractive index in this material, it allows you to calculate the angle at which total internal reflection is going to begin. So you'll notice I just want to make a very clear point here that I haven't put N1 here. It clearly is N1. It's this material, okay? But we always consider this to be our sort of vacuum. So when we mention refractive index, we're always talking about the refractive index of the material that we want to find the critical angle in. So it becomes pretty obvious when you see an equation like this that the critical angle is being calculated for the material that you're interested in. So that n must be the refractive index of the material that you're looking at. So let's have a bit of fun with this and see if we can turn it on its head and use the known critical angle to measure the refractive index of a material. So I'll draw this in front of you, and then maybe we'll go and do it in the laboratory together. So here we go with our glass block. Now remember, it doesn't need to be semicircular, but it just makes the whole thing a lot easier. Not necessarily easier to draw, you'll notice. Okay. So there's our glass block. And what we're going to do is we're going to fire light in, straight in. Well, there's no point in doing that because it comes straight out. Bigger angle, it will refract. Bigger angle, it'll refract. Bigger angle, and it's refracting. And then finally, at the critical angle, if we get the critical angle right, so I'll draw the normal on. Geometric optics, by the way, guys, geometric optics can all be done with sort of rulers and protractors and things. So if we get it just right and we open up this angle, so this angle here, theta, is equal to C. So we're at the critical angle. We'll have the light ray coming in. You'll notice, by the way, that that angle should be 90 degrees, so it just goes straight in. It's going to scoot along the surface at the critical angle. Okay, and you will get some partial reflection as well at this point. So I don't like doing this because it kind of messes up my diagram, and I usually make a terrible mess of it myself drawing it. But don't forget, you do get a little bit of light reflecting that way at that stage. Oh, I've got the angle a little bit on the small side there, but you get my idea. Okay, so what do we know here? Well, we can work out the angle by measuring it with a protractor. Okay, we know that out here this is N1, and we're going to make N1 equal to 1 because it's basically a vacuum, it's air. Okay, and air has a refractive index of about 1. Okay, often 1. It doesn't have a refractive index of exactly 1. It depends on all sorts of things, including its density and therefore its temperature. So when you see mirages or heat hazes, okay, that's the light refracting and refracting and refracting, going through different refractive indexes, changing direction a bit. Okay, but for the sake of this, we'll make the refractive index equal to 1. Okay, so we can set this up. We can get a laser beam, turn the angle until we just get that 90 degrees. We can measure the critical angle, and then we can calculate N2, the unknown refractive index. Okay, so you'll remember that, I'll just put the bit from our Snell's law down, yeah, that we got sine of the critical angle is equal to 1 over n. Okay, but this time it's n that we want, so n it is obviously N2, yeah, this one. N is equal to 1 over sine C. Okay, and that's quite an important formula. Okay, it's used an awful lot when we're trying to work out the refractive index of a material, assuming the outer material is basically a vacuum or air. So it's the equation we would use to find this N. This is the N in this material. Just to give you a couple of examples, and they vary massively, but N for glass varies on purpose because we want to use glass in optical instruments to bend light, to refract light. Is approximately 1.5. You can get higher and lower versions. And interestingly enough, for perspex, plastic, sort of acrylic plastic that we use in the lab these days, not when I was a student, because students can throw this stuff around and drop it on the floor and it doesn't shatter and it doesn't have sharp edges. It's about the same. Okay, so shall we head off into the lab, see if I can demonstrate refraction, total internal reflection, and see if we can work out what the refractive index is of our semicircular plastic blocks. Okay, so let's have a quick look at refraction in the laboratory. So I've got my plastic block here, and it's a higher refractive index, so it's going to cause refraction to happen. Put it in front of the array, and obviously the light goes straight through because it's hitting the block at the normal. But I'll just move it this way a little bit. But as I turn the block, and turn it, and turn it, and turn it, you'll notice a couple of things happening. Okay. Firstly, you should see it's very dim, but you'll see a bit of partial reflection there, so don't forget that. Obeys all the laws of reflection. And you can see where the ray changes direction. It changes direction entering the more dense or the higher refractive index material, and it changes again when it leaves it. And you'll notice that if we draw the normal on here, the ray bends towards the normal and then away from the normal. So that's a sort of classic picture of refraction. So let's look at total internal reflection in the laboratory. So I've got my plastic block here, and it's a higher refractive index than the air around the outside. So I'm going to put that in front of the beam. Okay, and you remember that this is part of a circle, so if that's the middle of the circle, this ray will enter at 90 degrees because it's along a radius. And there's no refraction there that you see, no angle change, but there is a change in velocity. It will be slower here than there because this is a higher refractive index than outside. Perhaps the refractive index, we can say, outside in the air is 1. So let's now turn the block. Okay, and as I turn the block, see what happens here to the refracted ray. So you'll notice the refracted ray getting closer and closer and closer to the surface of the block, and closer, and now there's a very large angle between the normal and the refracted ray. But if I start turning any more, we're almost there. There it is. Okay. In other words, the light ray goes in and reflects straight off the more dense material. The one with the higher refractive index would be better to say. So I find it absolutely fascinating that if I put my finger here, there's absolutely no light escaping from a totally transparent surface. And we can use this method if we measure angles to work out the refractive index of the more dense material, the higher refractive index, that of the plastic. Okay, so let's see if we can determine the refractive index of this plastic block in the laboratory. So to do that, I've got a sheet of paper here. Graph paper is sort of easier, and I'm going to draw on the direction that the ray goes. So I'm going to send the ray along this line here, and I'll draw it in red. So there we go. So that lines up with the laser beam. And then I'm going to put the glass block down here, And what I'll do is I'll draw where the back of the glass block is going to go. So to begin with, that's going to be at 90 degrees to the ray. There we go. And let's bring in the, I always say glass block, plastic block, whatever. Put that in there. And if you remember, because we're shining light into a semicircle, that's the centre of the circle, that's a radius, so the light goes straight in. It doesn't change direction, but it does slow down. And then what I'm going to do is just turn the block, and as I turn the block, you'll see the refraction happening, and I want to turn it through an angle when the light just scoots along the edge of the block, doesn't escape from it. Okay, so let's now turn the block. So I'll rotate it, and you'll see the refraction happening here. Okay, the angle getting bigger and bigger. And I'll keep turning the block, and keep turning and keep turning. So you can see we've got quite a large angle of refraction, but we still haven't got total internal reflection. We haven't reached the critical angle. Keep going. You'll see a bit of reflection here happening, but we've still got light coming out of the block, so it's not total internal reflection. Turn a bit more, and there we go. Okay, so you'll notice here, it always surprises me this, I always think it's wonderful. If I put my finger here, there's no light coming through at all. This is a totally transparent block of plastic, and yet the laser beam is completely, totally, internally reflecting off the inside of it where the boundary is. And remember, this is total internal reflection because it is going through a higher refractive index and hitting the boundary of a lower N. Okay, so now let's measure the critical angle. So we've got the back of the block here. There it is. I'll just extend that line. Don't really need to have the laser on now. Okay, and then I need to find the normal to that line. So there we go. Now I'm going to make a few little mistakes here on purpose just to make a point. So what I will do is I'll use quite a thick pen and I'll draw it fairly quickly. Okay, and then I will measure the angle. So I've got a protractor here, and what I'll do is I'll measure this angle, and I'll put the protractor down slightly off the centre here, slightly badly. I'm doing that on purpose to say I get about 48 degrees. Now that angle is a little on the large side. You might say, well, why are you doing this so badly? Because occasionally you get questions about talking about where the errors are. So I haven't quite lined this up. I've got a thick pen, and I can only measure on the protractor perhaps to the nearest degree. So I'm going to say that that's 48 degrees. Now, I think you can all see that that's a little bit on the large side. It's more like sort of 44, 43. But I'm trying to point out when we do the example on the board, if I use 48, I can then say to you, well, okay, why am I so far out? Where have I made lots of mistakes? Perhaps that's too big an error, but think about all the places where this could go wrong. I have actually sellotaped it down, and one of the things that happens, I'll tear it off, there we go, is the paper moves a little bit, etc. So it's good to see the experiment being done slightly badly so you can see where the errors are. So let's go through our results. So we found out there that the critical angle, so the angle that we measured, which is the critical angle, was equal to 48 degrees. So we know the refractive index, N, is equal to 1 over sine of the critical angle, as long as the material outside is a vacuum or air, has a refractive index of 1. Okay. And 1 over sine 48, so the refractive index is 1 over sine 48. and that comes out as N approximately equal to 1.3. Okay, so if you think about it, not only have we worked out the refractive index of the material by using the critical angle, and that's something we can measure in the lab, we could also work out the speed of the wave going through this material, because the speed of light needs to be divided by 1.3, so V will be equal to C divided by 1.3. So the speed of the waves in this plastic, just do that, 3.0 times 10 to the 8 divided by 1.3 is, hit the eng button, my favourite button on the calculator, 2.3 times 10 to the 8 metres per second. So we're almost there. Let's look at a really good use of total internal reflection, and that's for optic fibre, or you're going to call it fibre optics, what have you. Okay, this is the total backbone of internet communications, and not only internet, in fact. So what we use to communicate is we use light, and we send light down a fibre. And I've got a bit of optic fibre I bought when I was a kid. It was actually quite expensive. I remember buying it on Tottenham Court Road in London, which used to be full of sort of electronic shops. Now optic fibre is lying all over the place. But what I like about this bit is it's very thick, and it doesn't have a black plastic case on the outside. So I'll stick it on my projector and hold it up to the camera, and then I'll just put my finger over it. And it's probably out of focus, but I guess you can see it flashing. Okay. You can also see it's sort of coiled up. So even though it's coiled up, it's quite interesting because the light enters it and doesn't come out of the sides. Okay, it totally internally reflects inside. Now, the optic fibre I'll draw for you will be like this one. Okay, this is the sort of optic fibre that we used to use for interconnecting electronics. And it's really important that this one, I don't know if I can project, I usually project this for my students. You can see there's an outer plastic case that's black and an inner transparent core. Okay. Do not think for 1 minute that the outer plastic case is what causes the total internal reflection. It's not mirrored, it's not shiny, it's black. It's purely there to protect the fibre from scratches and things, because scratches would make the light hit the edge of the fibre at less than the critical angle. It's got to be done, hasn't it? Stick that on the projector, and again, there we go. Okay, and if I do this sort of thing, it's probably out of focus, but you probably see it flashing. I wonder what happens when I put it really close to the camera. Oh yeah, that's good. Okay, you can actually see a bit of red. It's the light going through the blood in my finger. It's not that the fiber's red. Okay. Now, if I could flash this with Morse code really rapidly, I could send you a signal, as long as you could decode it. Just before we do the physics of this, all of that fibre optic is not brilliant. It's incredible. I could go on for hours. It's incredibly complicated how this stuff works, but you actually find it works best when it's thinnest. And so here's a commercial piece of optic fibre. Okay, it's got a very tough outer core on it. This might be like your internet coming into your house, as a broadband or what have you. Okay, and TV. And inside it are some optic fibres. And what you're seeing there is mainly the outer coloured coating. I'm not going to call it insulation, so the engineers can decide which fibre they're looking at. Sometimes this does project. Yeah, okay. It projects with the disadvantage that I can't reach it. Okay, so there we go. Can you see the thickness of the outer casing? And that's there. That little chunk there is a little bit of fibre that's free that I've removed the casing from. Okay. Joining this stuff up is tricky. You have to basically, to join it, you have to strip off the coloured outer casing, line up two pieces of fibre under a microscope, and then usually you pass a very large electrical current through it, even though it doesn't conduct that well, or you heat it anyway and the glass melts and joins. Okay, JCB, cutting through optic fibre, or a digger should I say, it's not JCB's fault, is bad news because you will have sliced through it, and joining this stuff is tricky. So what I better do now is draw you a picture of optic fibre on the board and show you how it works. So I'm going to massively magnify this up, and if you remember, fibre optic works even if it's coiled up. It can't be coiled too tightly, but I will draw it like this. Okay, so this is the glass core, the bit that the light is going to travel down. Okay, but it's really important this. Do you remember that you only get total internal reflection when light hits a more dense medium? Okay, so out here we've got to have a less dense medium. Now you might say, well, we've got it already, we've got the air. But what we typically do is we have a layer of glass with an N that's higher, shrouded by another layer of glass. Don't ask me how they make this stuff, I can tell you, but they've got to make it very, very thin in the end. A second layer, which will be the lower refractive index. Okay, so we're sort of drawing it sliced in half here. Right, and then I showed you with, well, this one will do. Okay, I showed you that that could be the two pieces of glass or plastic. I've been meaning to do an FJ's video, physics video on this, and I've never got round to it. You noticed how thin, I'm going off on one now, aren't I? How thin this optic fibre is. It's often made of glass, yeah? Okay, and it's really interesting that if you take a rigid bar of glass and stretch it out and make it very, very, very thin, it becomes very flexible. It's quite interesting. I should do a video on that at some stage. Okay, so the outer casing, so it just doesn't get damaged when it's buried in the ground. There we go, around here. Excellent. Okay, so this bit here is the outer casing. I'll just quickly black it in, otherwise we'll be here all day. Some teachers will draw this end on, yeah? So you can see like a ring of outer casing, then a ring of material, I'll call that N1, and the fibre itself here, N2. Okay, and do you remember for total internal reflection, yep, N2 must be greater than N1. Okay, good. Very quickly, I'll draw some light in this. I won't draw the light coming in because things happen when the light enters, but here we go. There's some light. It's come from this direction. Okay, it's hitting the interface between N2 and N1 at an angle. There's a normal greater than the critical angle, so off it goes. Total internal reflection. Same again. You'll notice all these bounces are caused by the fact that the fibre is quite thick, okay, and secondly it's not straight. If you straighten it out, think about what the path lengths would be like. So reflection, 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 and we'll do that. So you imagine this light wavefront wave bouncing in and around here, reflecting and not escaping from the fibre until it hits the end. Now, I don't know if this would ever come up in an A-level, but be warned that when it leaves this, if it was to leave it like it did on my examples in front of the camera, then it has got to refract away from the normal because it's going into a less dense material. So if I was to draw that on here, I'd have the boundary here between the optic fibre and the air, and I'd have the ray, and I'd have to show it bending away from the normal. Finally, how is this used for communication? Again, don't start me because I could go on for hours here. Use a laser. Use a rapidly pulsing laser, so we can use laser pulses. Okay, and I'm sure you're aware that the internet and communications is usually digitized, and digitized means that whatever you're doing, whether it's colors, whether it's me talking, or whether it's computer information, that is all coded. It's incredibly interesting science, coded into a series of ons and offs. 0, 1, 0, 0, 1, 1, 0, 0, etc. Okay, so I'll just write underneath this, if that's the length of a binary digit, then that will be off, on, off, off, on, off, off. 1, 2, 3, 4, 5, 6, 7, 8. Oh, okay. Yep. An 8-bit word, 4 and 4, 2 bytes. Okay, anyway. Now, you can get your laser beam and go flash, 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 flash. Kind of Morse code, it's not Morse code. Okay, and when that comes out at the other end, all we need to do is to get a computer to know what this means. And maybe it means some numbers, maybe it means some sound amplitudes or frequencies. Yeah, or maybe it's some, did I say colour? Something we could have on a screen, okay? But this can be decoded. So we've used our optic fibre to, now listen to this. I was just about to say, we've used an optic fibre to carry signals around the world with lasers at the speed of light, which is phenomenal. It's about 7 times around the Earth per second. But be careful, okay? It is at the speed of light-ish, but remember that N2, apart from the fact it's not straight, okay, N2 will not be 1. So in fact, the laser beam goes down the optic fibre slower than the speed of light, but it might still be half the speed of light, which is incredibly fast communication down a very narrow fibre that can be laid in the ground. It doesn't involve satellites and things like that. And before I go off on a massive tangent, okay, we can send these codes down very compressed. Okay, we can send them down very fast, and we can send them down with different laser colours, so we can send multiple signals at once. We can multiplex the data we're sending down the optic fibre. So there we go. I hope you found that useful, the lesson on refraction and taking it further to total internal reflection and its uses. Anyway, I'll be making another video soon, and I look forward to seeing you then.